As we have learned throughout this program, we are continuously seeking to trip faulty segments of the system as rapidly as possible. We also want to protect 100% of the line by high-speed tripping instead of just 70 or 80%. This is particularly important for high-voltage transmission lines, where a delayed fault could conceivably cause instability of the system, resulting in tripping and clearance of many other transmission lines and generating stations. By using pilot protection, rapid tripping and clearance is achieved by allowing the relays at each end of the line to communicate with each other and compare conditions. As we shall see, there are many different ways of achieving this, including various types of communication channels. The basic types of communication used between each end of the line are solid metallic connection, power line carrier, microwave, or fiber optic cable. Let's first take a look at the solid metallic connection, generally known as pilot wire relaying. This is used where the distance between each end of the line is quite short, say up to 10 miles. Indeed, at this short distance, other forms of protection, such as overcurrent or distance relays, are not very effective. Why is this? The problem with the distance relay is that the short transmission line will have quite low impedance, and therefore the relay will not be sufficiently accurate. A tolerance of, say, 2 miles is not too significant where the lines are 50 miles long, but it is certainly not adequate for protecting a 10-mile line. With the overcurrent relay, the problem is that there is very little difference in the magnitude of fault current for close-in faults and for faults out on adjacent lines. For short lines, we could consider differential protection with the CTs at each end of the line interconnected by pilot wires. We can well imagine the differential relay connected like this at the center of the line. Employing the well-known differential principle, this would compare the current entering the line with the current leaving. For normal operation or even a through fault, these currents would balance and no current would flow through the relay operating coil. However, in the event of any internal fault, this balance would be upset and current would flow through the relay operating coil and trip the breakers at each end of the line. In practice, this is not how it's done. Instead, we have a separate relay at each end of the line, and these are interconnected by the pilot wire, as we see here. The relays are fitted with restraining coils which try to hold the operating contacts open, while the operating coil tries to close them. Let's consider the case where there is an external fault, that is, a through fault. The current in the CT secondaries circulates like this. There will probably be a small current passing through the relay operating coils, but this is insufficient to overcome the restraining coils. In this situation, the relays will not trip their respective breakers. This is correct for a through fault. Now, in the case of a fault within the protected line, the current will feed in from both ends. Now we have a large secondary current flowing through the operating coil, and this will be sufficient to operate the relay. Both relays operate to trip the breakers at each end of the line, so we have rapid clearing of the fault. In most circumstances, the magnitude of current feeding in from each end of the line is not identical. The exact value depends upon the location of the fault and also the amount of fault current available from the source at each end. For this reason, a small amount of balancing current will still flow through the pilot wires. An extreme case would be when there is no inflow of current from one end, say from bus H. All the fault current is now fed from the source at bus G. The CT secondary current will now flow along the pilot wires and pass through the operating coils of both relays. So it will still achieve the protection scheme's main objective, That is, to trip the breakers at both ends of the line simultaneously. This type of arrangement can be extended to include a third terminal, like this. This simplified schematic explains the principle of pilot relaying, but as you would expect, in practice it is more complicated. Here is a typical arrangement, which is commonly used on pilot wire schemes. At each end of the line, CTs are connected to each phase, and these are fed into a common sequence filter. This filter actually measures and converts three-phase currents into a single-phase output, which represents both positive and zero-sequence components. Polarity and the phase angle of the voltage depend upon the direction of primary current flow through the CTs. This output is fed into a saturating transformer. The purpose of this is to limit the voltage output to about 15 volts, no matter what type of fault is involved. This voltage produces a current flow through the relay and along the pilot wires to the equipment at the other end. Usually, the pilot wires are insulated from the relay circuit and the CT secondary circuit by an insulating transformer. At the same time, this raises the voltage from 15 volts to about 90 volts, so providing for more positive circulation of current. Where the fault is external, that is, a through fault, the sequence filter at this far end will produce a terminal voltage, which is of the opposite polarity. So the current circulates around the pilot wire circuit and through the restraint coils, but not through the relay operating coils. This is correct. Now, for a fault within the transmission line, the voltage produced by the far end sequence filter will be of the same polarity. Therefore, current will flow through the operating coil of both relays and trip both breakers. This system is known as phase comparison. We are comparing the phase angle of the voltage which is produced at each end of the line due to the fault. Now remember, these pilot wires are running either underground or perhaps along distribution poles, and they may possibly become damaged. What would happen if the pilot wires became open-circuited? Well, in this case, if an external fault occurred, both relays would operate. So this is one disadvantage. Perhaps a bigger problem is the case of a short circuit between the two pilot wires. This would effectively short out the operating coils of each relay. In the case of a transmission line fault, internal or external, all of the secondary current would flow through the restraint coils and so make the relays ineffective. The fault would not be cleared. In order to detect pilot wire faults, such as open or closed circuits, sometimes a monitoring system is installed at each end. A DC milliamp signal is applied to the pilot wire circuit. The capacitors allow AC circulating current to pass, but block DC. Pilot wire faults alter the DC signal and cause an alarm. Another method, described in your workbook, measures the actual circulating current in different parts of the circuit. The pilot wires are usually quite heavy to provide mechanical strength and keep the resistance between the two terminals at a reasonable level, about 2,500 ohms. The two conductors are always twisted together to form a pair because this reduces the interference due to inductance from nearby signals and external voltages, such as the power line itself. The pilot wire is often buried in the ground and protected by shielding, which will, of course, be at the potential of the surrounding earth. Even so, the pilot wire conductors may be subjected to high voltage due to mutual inductance from a nearby transmission line under fault conditions. For this reason, adequate insulation must be provided in the pilot wire cable. However, even a small induced voltage in the pilot wires may be sufficient to cause misoperation of the protection relays. Therefore, it is usual to provide at each end of the pilot wire a mutual drainage reactor, which will effectively discharge the high voltage to ground. A typical system uses a gas discharge tube like this. The reactors add equal impedances to the drainage circuit and ensure that both conductors flash over simultaneously. Otherwise, the voltage difference could cause operation of the relays and unnecessary tripping of breakers. The flashover voltage is about 500 volts. The drainage reactor is usually grounded to the surrounding earth instead of the substation ground mat, and we'll see why in a moment. The earth is commonly known as a remote ground to distinguish it from the station ground mat. A voltage difference can arise between these two grounds if a ground fault occurs on the power line. As fault current flows through the earth, the ground resistance and the resistance of the station ground produces a voltage drop and raises the potential of the station ground mat. So now we have a difference in voltage between the ground mat and the pilot wire shielding. In fact, if this shield was connected to the ground mat, it is probable that the large fault current from the power line would try to flow along this shield and cause damage to the cable. For this reason, the shielding is terminated outside of the ground mat area. Likewise, when grounding the drainage reactors that we just mentioned. However, we still have a problem. When the two pilot wire conductors enter the station, they will be connected to relays which are usually grounded on one side, so one of the pair will be subjected to the rising ground mat potential. The difference in voltage between the two conductors may cause inadvertent tripping of the relays. This problem is resolved by installing a neutralizing transformer, which in effect raises the voltage of both conductors to compensate for the difference. The primary of the neutralizing transformer is connected between the station ground mat and the remote earth, so registering the difference in potential. And remember, this usually occurs only when a ground fault exists on the power line. The neutralizing transformer has two secondaries, each of which are connected in series with each conductor of the twisted pilot pair. Now, as the voltage across the primary rises, it superimposes the same voltage on both conductors. When you are working around this equipment in the field, always remember that the remote earth may be at different potential to the station ground. Be careful not to place yourself across these two potentials. So we can see that the simple pilot wire system is not so simple after all. A considerable amount of equipment is required at each end of the pilot wire. We need the sequence filters, the saturating transformer, the actual tripping relays, the insulating transformer, and then protection for the pilot wire itself. That is, the neutralizing transformer and the mutual drainage reactors. In many installations, DC polar type units are used in pilot wire protection systems because of their high sensitivity and high speed. In this arrangement, the appropriate circulating current is rectified in two separate units, and the resultant DC passed to the operating coil and the restraint coil. These two coils are wound in opposing directions on the same core or armature. The armature is placed within the field of a permanent magnet. The only flux present is that produced by the permanent magnet when there is no current flowing in either the operating or restraining coils. The armature does not move. The situation does not change when current flow is such that the strength of the operating and restraining coils are equal, since the flux produced is in opposite directions and cancels out. When current flow is such that the flux produced by the operating coil is greater than the flux produced by the restraining coil, the armature will move, so closing the tripping contacts. The tripping point can be adjusted here. In the pilot wire protection scheme that we have just studied, the current flowing in the pilot wire is actually 60 hertz AC current generated by the fault current flowing in the power lines. Another scheme using metallic conductors transmits a signal along the pilot line at higher frequency, 1,000 to 3,000 hertz. And we'll be looking at this in a later segment. As we have already mentioned, pilot wire protection is limited to a distance of about 10 miles. But most of our power lines are much longer than this. So other forms of communication channel are employed for pilot protection, and we'll be looking at this in the next segment. For now, time to take a break. Please switch off the tape and review this material in your workbook. We have already pointed out that several different types of communication channels can be used to interconnect relays at each end of the line. The pilot wire system that we discussed in the last segment is really only practical for short distances, up to about 10 miles. Above this distance, most of the pilot relaying schemes use power line carrier or audio tone facilities to communicate. In the power line carrier system, the signal is transmitted at a specific tuned frequency selected within the range 30 to 500 kilohertz. This high-frequency signal is superimposed upon one of the power line conductors, usually the center conductor, so as to reduce the effect of mutual inductance. The power conductor provides the metallic path for the signal. The power line, in fact, is carrying, say, 200 megawatts of power at 60 hertz and 10 watts of signal at 250 kilohertz. The first question is, how do we confine this high-frequency signal to the line itself? How can we prevent it from escaping into the bus and the power network at each end? This potential problem is resolved by fitting line traps in series with the line at each end to block the flow of high-frequency current, that is, the signal. The line trap consists of a capacitor and reactor in parallel to form a resonant circuit. This is tuned to provide zero impedance to 60 hertz current, but to provide a very high impedance, almost open circuit, to the 250 kilohertz signal. You will remember that resonance is achieved when the inductive reactance of the reactor is the same value as the capacitive reactance of the capacitor. This is because the two reactances are opposing. The phase angle of the inductive reactance is at plus 90 degrees, while the phase angle of the capacitive reactance is at minus 90 degrees, as shown here. Now remember, the value of reactance in both cases depends upon the frequency. Inductive reactance XL equals 2 pi times frequency times the inductance. So as frequency goes up, so does the reactance. In the case of capacitive reactance, this is equal to 1 over 2 pi times frequency times capacitance. In this case, then, as the frequency increases, the capacitive reactance decreases. The actual values of inductance and capacitance are chosen so that their combined reactances provide a very low impedance at 60 hertz. However, when frequency is increased to the carrier frequency, the value of inductive reactance increases immensely, while the value of capacitive reactance falls to a very low value. This circuit now provides high impedance to the carrier frequency signal, but low impedance to the 60 hertz currents. It effectively blocks the escape of the high frequency signal. As the line traps are placed in series with the power line, The equipment, that is, the reactors and capacitors, must be very robust and capable of passing high fault currents, say 60,000 amps. Now let's look at transmitting and receiving. The carrier signal is generated in the transmitter, and this itself is triggered by the protective relaying scheme. In order to inject the high-frequency signal into the high-voltage power line, a coupling capacitor is used. This is a large, high-voltage capacitor, which is capable of withstanding the power line voltage under both fault and switching surge conditions. This effectively provides the insulation of the high-voltage line at, say, 230 kV from the low-voltage transmitting equipment, say, 120 volts. The value of the capacitor is selected so as to provide high impedance to the 60 hertz line current. For example, let's say the capacitor has a capacitance of 0.02 microfarads, that is 0.02 farads divided by 1,000,000, or 10 to the 6th. At 60 cycles, the capacitive reactance would be 1 divided by 2 times pi times 60 cycles times 0.02 divided by 10 to the 6th. This all works out to about 133,000 ohms, an extremely high impedance, which would certainly block the flow of 60 hertz current from the line. On the other hand, at the signal frequency of, say, 200 kilohertz, that is 200,000 hertz, the capacitive reactance works out to about 40 ohms, a low impedance which allows the flow of high-frequency signal. This impedance is even further reduced by adding a reactor in series. The reactor can be adjusted, that is, tuned, so that its value of inductive reactance is the same as the capacitive reactance, 40 ohms in this case. So this presents almost zero impedance to the flow of the 200 kilohertz signal. By tuning the reactor, we can select the coupling circuit to pass specific carrier frequencies as desired. This circuit is logically called the line tuner. At the receiving end of the line, a similar coupling capacitor and tuner are installed, connected to the receiver. Provided the line tuner is adjusted to the same frequency, the transmitted signal flowing along the line will now pass into the receiver for appropriate action. Both the transmitter and a receiver are installed at each station at both ends of the line. In the on-off system, the receiver is normally on, waiting to receive a signal on its tuned frequency. When the protection relay, say a distance relay or an instantaneous relay, detects a fault, it switches on the transmitter, which then begins to send the signal at the preset frequency. The receiver picks up the signal and initiates appropriate action by energizing the control circuit. We'll be talking more about this in the next segment. This method of transmittal is known as on-off because the signal is only transmitted when action is required. Another method more commonly used today initiates a change in signal frequency to produce action at the far end. In this arrangement, under normal operating conditions, both transmitter and receiver are switched on all the time, and a signal is flowing continuously at a specific frequency. When the relay detects a fault, it will switch or key the transmitter to a different frequency. This is known as shift keying the frequency. The receiver at the far end responds to the change in frequency and initiates appropriate action. This system is called FSK, frequency shift keying. It has the advantage that if the communication equipment fails at any time, loss of the continuous guard signal will be noticed and appropriate action taken. Another application of the FSK system uses audio tones. This method works by changing frequency, but the actual range of frequency used is much lower, about 600 to 3,300 hertz. This is within the sound range of the human ear, hence the term audio tone. We are all used to hearing these audio tones when using the telephone. The audio tone system provides the same high reliability as FSK by applying a continuous guard signal and a trip signal at a different frequency when required. The frequency shift between guard and trip signals is known as the bandwidth. For example, a typical bandwidth of 170 hertz may give us a guard signal of 1360 hertz and a trip signal of 1190 hertz. In this case, the nominal channel frequency would be halfway between the two, that is 1275 hertz. For short distances up to 10 miles, the audio signal is sent over solid pilot wires. Nowadays, fiber optic channels are often employed for distances up to 30 miles. Microwave or lease audio tone telephone facilities are used when the distance is longer. We'll be looking at the application of these different schemes in the next segment. For now, we're looking only at the communication channels themselves. Okay, let's now take a brief look at radio communication by microwave. In this system, the signal is carried at a much higher frequency, that is between 3,000 and 12,000 megahertz. This super high frequency signal, SHF, is transmitted by radio from terminal to terminal. At each terminal, a dish antenna is installed, and the transmission must be by line of sight. The super high frequency waves travel only in a straight line. They do not follow the curvature of the earth. Therefore, for long distances, many repeater terminals are required. We are all familiar with the dish antennas that we see on high ground dotted across the country. In any particular power company, the microwave communication system will be used for many different functions, such as voice communication, data communication, information transfer, loading instructions, switching instructions, and protective relaying, all operating at different specific frequencies. The microwave system has the advantage that it can accommodate a huge number of channels. This is accomplished by the technique of multiplexing. If you would like more information on this subject, please refer to the L&K videotapes in the distribution and power system programs. Another communication channel which is rapidly being introduced into the power system is that of fiber optics. In this arrangement, the signal is transmitted by light waves traveling through an optical fiber. The fiber is made of non-conducting material, so it cannot provide a path for electrical signals. At the transmitting end, the electrical signal, perhaps a tripping signal from a relay, is converted into a beam of light. This travels down the fiber like this. The signal is able to travel around bends, providing they are not too acute. At the receiving end, the light beam is converted back into an electrical signal to initiate action, say tripping of a breaker. Obviously, the inner surface of the fiber has to be reflective, and its surrounding cladding is specially made to prevent or at least reduce loss of light. An advantage of modern fiber optic communication is that the attenuation of signal, that is the loss of signal, is much lower than in other forms of communication. The fiber optic cable is made of glass or silica or a special plastic. It is very expensive, and so it must be handled with care during installation or repair. Special splicing techniques are required to join sections of cable. One disadvantage is that a buried cable may be subject to damage, and each additional splice for repair can significantly reduce the signal strength. One method to reduce this kind of damage is to run the optical fiber cable in the air, supported by a power conductor or perhaps the ground wire. The insulating properties of the fiber cable provide a great advantage as it protects the signal from lightning, radio interference, and induction. It also protects the signal from ground potential rise at the substation. This eliminates the need for neutralizing transformers and other terminal equipment that we discussed earlier in this tape. A high-quality optical fiber link can transfer ultra-high frequency signals as high as 100,000 gigahertz. This means that one fiber optic link can carry a huge number of communication channels. The optic communication channels are typically installed in place of twisted pair solid conductors for pilot relaying up to about 30 miles. They are often used in conjunction with audio tone signals. So, that's a general look at the different types of communication channels that are used in pilot protection. In your workbook, you'll find a summary of the main features of these communication schemes. Take your time to study this information. And now at this point, let's take a break. Then we shall come back and see how the various protective relaying schemes at each end of the line utilize the communication channels to either trip or block tripping of line circuit breakers. For now, switch off the tape and review this material in your workbook. The main feature of pilot protection is that it operates over distance. We have already seen that different types of communication channels and type of signal can be used between the stations. Let's now look at some typical applications. One of the most basic is the direct transfer trip. In this arrangement, operation of local protection relays, say adjacent to a transformer, will cause tripping of a breaker at some remote location. You will remember that we discussed this in an earlier tape. Other applications for the direct transfer trip are A, shunt reactor protection where there is no local breaker, B, remote breaker failure protection, and C, line protection. We'll look at this in a moment. This diagram shows the arrangement for a transformer with no local breaker on the high voltage primary. Operation of the differential relay 87 initiates a signal to trip the line breaker at the remote substation. As there is no supervisory relay at the breaker end, this is known as direct transfer tripping. For short distances, the tripping signal would probably be DC over a solid pilot wire. For longer distances, PLC or audio tone systems are generally employed using FSK. Another application of direct transfer tripping is for protection against breaker failure, as shown here. Let us assume a relatively low-level fault on feed number 1. Breaker 1 trips correctly, but breaker 2 fails to open due to a mechanical problem. When the breaker failure relay 62 operates, it initiates tripping of breaker 3. It also sends a signal to the carrier transmitter, and this shifts frequency from guard to trip. At the other end of the transmission line, the trip signal is received and initiates high-speed tripping of breakers 4 and 5. For security, 2 channels are often used. The breaker will not trip until a trip signal is received over both channels. On underground systems, power line carrier is more difficult to apply due to the high capacitance of the cables. In this situation, the security of FSK is obtained by using audio tones transmitted over a fiber optic communication channel or a leased telecommunication facility. Now let's turn our attention to line protection. We have discussed in earlier tapes the problem in trying to obtain 100% high-speed protection of the line. For example, with the distance relay, the high-speed first zone element is normally set to cover about 80% of the line. If a fault occurs within the remaining 20% of the line, then the breaker will trip on the second zone, but this will be time delayed. Even with distance relays at both ends of the line, the problem persists. In this instance, breaker 2 trips at high speed on the zone 1 element of the number 2 distance relay. But the clearing of breaker number 1 still has to wait until the zone 2 element at this bus has timed out. With instantaneous overcurrent relays, we have another problem. Due to their lack of high precision, the instantaneous relay is set to cover only 80% of the line. This is necessary to prevent the relay overreaching into the next section of line. Pilot relaying helps us achieve high-speed protection on 100% of the line. There are several different methods of applying pilot protection, as we'll see. Let's look at an example using distance relays, bearing in mind that a similar arrangement could be made for overcurrent relays. Here, the distance relays, Zone 1, are set to cover 80% of the line from their respective ends, and therefore overlap. If a fault occurs within this overlap section, then the relay at each end will operate and immediately trip both breakers, so providing high-speed tripping. If the fault is external to the line, we do not want the relays to operate. Therefore, directional relays must be used with the tripping direction looking into the line. So this provides selectivity. Now let's look at a fault in the last 20% of the line. In this situation, the Zone 1 element of the distance relay located at bus G, let's call this station G, will not operate. The fault is outside of the preset zone. The Zone 2 element detects the fault, but tripping of breaker 1 is delayed. Preferably, we want high-speed tripping. Let's look at the other end. Station H. Here, the fault is close in, so the relay does operate and immediately trips breaker 2. At the same time, it immediately switches the transmitter from guard to trip frequency. This new frequency is sent along the communication channel. At station G, the receiver picks up the signal and immediately trips breaker 1. So this arrangement achieves the objective of high-speed tripping at both ends, and at the same time it prevents overreach and false tripping for external faults. Note the main characteristics of this protective scheme. The transmitter is working in the FSK mode. The relays are set to underreach. The signal is used as a direct transfer trip. The relays must be directional. This scheme is known as the directional comparison underreaching system. In practice, the protective package at each end would probably include ground overcurrent relays, as well as distance relays for phase protection. The operating diagram that we have shown is a very simplified schematic. More often, you'll find a logic diagram applied instead, like this. This is the logic at station G, connected by the pilot communication channel to the logic at station H. The protective relays are referred to as fault detectors. With a fault in the last 20% of the line, the fault detector at station H recognizes the fault and sends a positive signal to this box, which is marked OR. The signal passes through the box and goes on to trip breaker number 2. The OR designation means that the breaker will also trip for a signal coming in from the receiver. Either one of the signals will cause the breaker to trip. That is, one or the other. At the same time, FD2 switches the transmitter from guard to trip. This immediately starts transmitting across the communication channel, where it's received by the receiver at station G. The receiver sends the signal to the OR box, where it passes through to energize the trip circuit of breaker number 1. Note that it does not need a signal from fault detector 1. It is a direct transfer trip. However, if the communication channel fails and the fault detector at 1 operates after a time delay, then that will pass through this box to trip the breaker. Now, this is a relatively simple logic diagram and hardly seems worthwhile. But in a more complicated system, this is the best method of working out how the protection scheme functions. In fact, when designing the system, the logic diagram is usually prepared first. The electrical circuit is then designed to meet the objectives of the logic diagram. You must become familiar with this type of presentation. It's used extensively in connection with solid-state relaying. We noted in studying the directional comparison scheme that if the communication channel fails to transmit the signal, then breaker number 1 will not trip at high speed. It will have to wait for backup protection to operate, typically the second zone element of the distance relay. A bigger problem is that the communication channel may receive unwanted signals, perhaps by interference from other communication channels. This could cause the breaker to trip incorrectly, that is, when no fault exists. One way around this problem is to use signals for blocking instead of as a transfer trip. In this arrangement, in order to achieve the objective of protecting 100% of the line, the relays, that is, the fault detectors, are set to overreach into the adjacent sections of line. The pilot relaying system functions to block tripping when the fault is external. Let's see how this works. Again, directional relays are used at the end of each line, and this system is called the directional comparison overreach. Now, suppose we had an external fault to the right of bus H, but quite close in. The fault detector at station G would register this fault and attempt to open breaker number 1. At the other end of the line, fault detector 2 at station H does not see the fault because it's looking into the line. So it makes no attempt to trip breaker 2. But look, we have additional relays. These are known as starter relays. Their function is to switch on the transmitter. But note this important feature. The starter relay is looking out of the line, that is, in the opposite direction to the fault detector. The starter relay may be an instantaneous overcurrent relay, or perhaps the third zone of a distance relay wired to look out of the line. Either way, the starter relay must be set to see farther along the adjacent line than the fault detector. Now, the logic diagram. When the external fault comes on, the starter relay at station H operates and sends a positive signal to the AND box. However, fault detector 2 has not operated, so it is not sending out a positive signal. Note on the diagram the 0 number at this input. Convention tells us that the logic circuit reverses the signal. That is, a 0 input signal reverses and becomes a positive signal. As this logic box shows, and it requires 2 positive input signals, one from the fault detector and one from the starter relay. With these 2 positive signals, it initiates transmission of the blocking signal. This is received at the other end, station G, and the signal is passed into the permissive tripping circuit and mixed with the signal from fault detector 1, which, as you remember, is trying to trip breaker 1. The positive input signal from the receiver becomes a 0 signal. As this logic box shows AND, it needs 2 positive input signals, one from the fault detector and one from the receiver. But at this moment, it has only one, that from the fault detector. so the breaker is blocked from tripping by the transmitted signal. To give time for signal transmission and logic circuit operation, the tripping circuit is fitted with a timer. So for this external fault, no tripping would take place. Now let's see what happens with an internal fault. Both of the fault detectors sense the fault and initiate action. Let's look at station G. The fault detector, FD1, will register the fault at station G and send a positive tripping signal to the tripping logic. Remember, this needs two positive signals. As the fault is internal, the starter unit, S1, will not switch on the transmitter, so no blocking signal is sent to station H. Let's transfer our attention now to station H. Here, the same thing happens. The transmitter does not switch on, therefore no signal is transmitted to station G. Back at station G, the zero signal reverses and gives us the equivalent of a positive signal in the tripping logic. Now we have the two inputs, hence the tripping circuit is energized. After the timer has timed out, the breaker number 1 will trip. Identical operation to this takes place at breaker 2. In this scheme, if the communication channel fails to transmit, then tripping will still take place for an internal fault. However, it may also take place, but incorrectly, for an external fault, as there is no blocking signal. Take your time to go through the circuit and logic diagrams in your workbook. For now, switch off the tape and thoroughly go over this material in your workbook. A variation of the overreach scheme that we studied in the last segment uses frequency shift keying, FSK, of the transmitter instead of the on-off mode. This can be transmitted over PLC or by means of audio tones over a suitable channel. Let's look at the arrangement for PLC. The transmitters are switched on all of the time, and a signal is transmitting continuously to the other end of the line. Actually, the two transmitters and their associated receivers at the other end are tuned to two different frequencies, usually within an interval of about 1 kilohertz. This prevents a transmitter from inadvertently tripping its own breaker. The continuous signal, known as a guard signal, is a blocking signal which prevents operation of the relays under normal operating, that is, no fault conditions. As the transmitters are continuously on, there is no need for starting relays. Now let's look at the case where a fault occurs on bus G. The fault is close in but upstream to the breaker number 1. The fault detector, which is a directional distance relay, will not operate for this fault upstream. So the transmitter at station G continues to send its blocking signal to station H. However, the fault detector at bus H does register the fault because, remember, the relay is set to overreach into the next section. However, this will not trip breaker number 2 because of the blocking signal being received from terminal 1. Operation of the fault detector at bus H also keys the transmitter at station H to change its transmitting frequency from the guard signal to the trip signal. This is usually achieved by lowering the frequency by about 200 to 500 hertz. At the same time, signal power is increased from 1 watt to 10 watts. When this signal is received at station G, the relay is released to operate. But as we have just mentioned, this relay, FD1, does not register the upstream fault and therefore will not trip. In effect, the transmitted signal is applied as a permissive, which allows the relay to trip when the fault is within the protected zone. Now, let's look at the case of an internal fault.
let's say halfway along the line. At station G, the fault detector detects the fault and keys the transmitter to change frequency to the unblocked mode, so giving permission to the relay at station H to operate. This relay detects the fault and therefore operates to trip breaker number 2. At the same time, it keys the transmitter to key the unblocked signal to station G. This gives permission for the relay at this end to trip breaker number 1, so clearing the line.
This method of communication, utilizing the shift in frequency, has two distinct advantages. First, because the transmitter is transmitting continuously, there is no need for a starter relay to switch the transmitter on. Also, if there is a failure in the communication channel, the loss of guard signal will be immediately recognized at the receiver end. This condition will be alarmed so that the appropriate action can be taken.
While this is being done, the pilot relay system will be inoperative, but the distance relays will still be allowed to operate individually. Where the signals are transmitted by an audio tone system, the operation is similar. The shift in frequency is within the range of 150 to 500 hertz, and the signal power is increased by 12 dB.
All of these schemes that we have looked at so far are directional comparison schemes. They compare the direction of current flow at each end of the line by the use of directional relays.
Another method uses phase comparison in order to compare fault current flow at each end of the line. This method is often used where CTs only are available. Therefore, it is usually employed with instantaneous overcurrent relays as fault detectors. You will remember that we looked at a phase comparison scheme when we studied the pilot wire arrangements earlier in this tape. A similar arrangement is employed, but using power line carrier as the communication channel. As before, a special filter circuit is connected across all 3 CTs. If a phase fault or ground fault is present, this filter will produce a single phase voltage at its output terminals. The polarity of this voltage depends upon the direction of the current flow into or out of the power line. Actually, the voltage produced by the network circuit is not a sine wave, but a half-cycle square wave, like this. The transmitter is an on-off type, therefore a starting relay is required. The overcurrent relays are set up like this. The trip relay is set to overreach into the adjacent line. This is the element which is used for tripping. The starter relay is set to overreach further into the adjacent section, and this is operated without time delay to start the transmitter. So let's look at an example where the fault is to the right of bus H, but close in. This fault is detected by both trip relays at station G. The starter relay starts the transmitter to send the half-cycle square wave signal along to the receiver and tripping logic at station H. The overcurrent relays at station H operate as non-directional. This starts the transmitter, and at the same time it sends a tripping signal into the logic circuit, attempting to trip breaker 2. This trip logic receives yet another signal from the network's squaring amplifier. With external faults, that is, with both currents flowing this way, the signal from the amplifier is of the same polarity as the wave transmitted from station G. The signal received from station G is reversed. Hence, these two cancel each other out. Thus, only one positive signal is present and no tripping will take place. Breaker 2 remains closed. This same operation takes place at the other end. Even though the fault detector tries to trip breaker 1, it is prevented from doing so by the blocking signal which is received from station H. Let's see what happens in the case of an internal fault. In this case, the polarity of the square wave from the network circuit will be out of phase with the signal received from the other end. In fact, the two will be additive, hence tripping will occur at both ends of the line. Once again, let's examine the characteristics of this scheme. The transmitter operates in the on-off mode. Non-directional relays are used, hence the protection scheme is suitable for application with instantaneous overcurrent relays only. No voltage source is required. The relays are set to overreach, and the transmitted signal is a blocking signal. If the communication channel fails, the protection system will still operate, but it will trip incorrectly for external close-in faults. In all of these pilot protection schemes, the logic circuit is quite complicated. Solid-state circuits are frequently employed, although complete electromechanical installations are still widely used.
Now, at this point, let us summarize the different ways in which pilot relaying is applied.
The signal itself, this can be transmitted in the on-off mode. Once the transmitter is switched on, it sends a preset signal on a specific frequency to the receiving end. The receiver is continually switched on and tuned to the specific frequency, waiting for the signal. When the signal is received, it triggers appropriate actions. Alternately, the signal can be sent by the FSK frequency shift method. Here, a guard signal is continuously transmitted at one particular frequency, and then, when action is required, the transmitter is keyed to change frequency. The receiver detects this change of frequency and initiates appropriate action.
The FSK system is the preferred method nowadays, as it's more reliable due to the continuously monitored guard signal. In contrast, the on-off system must be checked at regular intervals, say monthly, to ensure that it will work when required. The signal itself may be used in several different ways.
To initiate tripping, that is, direct transfer tripping. To block tripping, or to permit tripping.
In your workbook, we have included a summary of the various pilot protection schemes in common use and their preferred communication channels. Take time to study and learn this information, and make sure that you study the pilot protection schemes that are used in your own power system. Check out the relay settings and also the logic diagrams with your supervisor. Please switch off the tape now and thoroughly review this material in your workbook.